So today I'm going to talk about some work that we did in collaboration between my home institution, Hochschule Luzern, and Roche Diagnostics International. So this is not entirely typical because I'm going to start with a statement of the problem, and then I'm going to give the background that is necessary to understand it. This is not very pedagogical, but it's actually how things developed in the project that I'm using as a case study here. Then I'm going to present the analysis that we performed and draw some conclusions. So me and my colleagues received a data set from an end-of-life sensor study, which contains experiments with 3 old and 7 new sensors over a time range of 1 month. These are roughly 1,200 measurements from an ion-sensitive sensor, both with known blood and quality control solutions. So for each measurement, we have the following information. We have the expected target values for the concentration. We have the type of sensor, whether it was old or new, and the type of solution, whether this was blood or a quality control solution. And then, most importantly, we have a time series of the sensor voltage, which includes calibration information. So when a measurement is performed, actually a 3-phases cycle starts. First, we have that the base voltage is measured before the sample is actually measured. Then we have the sample measurement, and we record the voltage for a certain time. And then the base voltage is measured again after the sample has been removed. And this can be repeated at regular interval times. Now, with these data, we were given the following problem. So we wanted to, on one side, we had to probe the precision limitations of the instrument that generates this data. And on the other hand, we wanted to perform a feasibility study of skipping the part of the measurement after the sample was measured. So our stakeholders, besides giving us these goals, actually gave us quite an important message, which is that they were not really interested in having a full machine learning solution which will solve the problem end to end, but they actually wanted to understand how to combine physical models with machine learning and possibly getting some insights on their data set. Now, since we had to do this combination between machine learning and physics, we actually went back one step and tried to get some relevant background. So the instrument the data comes from is the one that you can see here in the figure, and it's used mostly in intensive care and emergency units. It measures blood gases such as oxygen and carbon dioxide, acidity of blood, so pH, a bunch of electrolyte concentrations, metabolites, and so on and so forth. The principle it works on is the one of an electrolytic cell, which is governed by the Nernst equation. Essentially, what this means is that the logarithm of the concentration is given by this linear formula that you can see here, where actually K is a calibration parameter known as the slope. Then we have U, which is the voltage measured when the sample is in place, U naught, which is the base voltage, and C naught, which is the base concentration. And here we see already one problem, that is that this formula has a unique value for U naught and C naught, but actually the voltage measured before the sample and after the sample should both be base voltages and should be U naught. So this formula does not have a straightforward interpretation in terms of the data that we actually receive. Now, with this background, we can go back to our data and actually start our analysis. So first of all, I want to point out that this data set only contains data from 10 sensors and 1,200 measurements. In terms of machine learning, this is a fairly small data set. And moreover, the rather atypical characteristic of this data set is that each measurement contains a whole time series as a feature. Now, if we provide this data to the model as unstructured input, actually what the machine learning model has to do is to learn that these are sequential points. And by the time it does it, it has exhausted all of the information contained in the data. So in this case, it's actually practically mandatory to use some domain knowledge and provide the input in a format which is informed by physics. In this case, what we know is that the potential should converge with time to certain value. So actually we encode this time series information in a convergence value in the range of values from the beginning to the end of the time series. in the speed of convergence and in potential oscillations that can occur around the expected behavior. So we want to start with the simplest thing that we can do. And this means that we're going to take the features that we just constructed, use them as inputs, and try to regress the target concentration that the instrument should measure. Luckily, nowadays, there are frameworks which allow us to compare many different machine learning models with very little effort. In our case, we actually used PyCaret to essentially run a number of models, including many variants of linear regression, k-nearest neighbor regression, tree-based models, both including bagging and boosting, and neural networks. Note that since the size of the data set is rather limited, we already expect that neural networks are not going to perform particularly well in this case. Now, indeed, what we see in this first very simple task is that linear models perform best, and the results can be seen in the histogram on the right, which is a histogram of the percentage error on the measurement. In blue, you have the histogram of the results from the current standard measurement procedure. And in green, you have the histogram of the results from the linear model that I just mentioned. These histograms can be summarized with a single number using root mean squared precision error, which is roughly speaking the expected percentage error on the measurement, which is 3.4% for the current procedure and 2.7% for the linear model. So this is sort of to try to get to grips with the data, but of course, we're not going to stop here. And what we actually want to do is to combine physics with machine learning. So one of the very simple ideas that one could try to use is to use the result of the Nernst equation, the result of the standard measurement, as a feature for machine learning models. So if we do this, we notice that nearest neighbor and tree models obtain an almost perfect performance with an error that is below 1%. This is highly suspicious, and this is a result that in the end is too good to be true. So what one should do at this point is actually to inspect results. And this is what we've done here. And on the bottom right, you can see a plot of the predicted values of concentration against the target values of concentration. And what we notice is actually that only a limited set of values are allowed for target concentrations, and that our model is predicting these values spot on for many of them. So in the end, ultimately, this is an artifact of the data that our model is learning by heart. This is not what we want to learn, and this tells us that we should take extra care when dealing with data sets that were not collected for the purpose of machine learning. Now, of course, we're not going to give up, and we try to inject the same knowledge in machine learning from physics in a different way. So we take, in this case, the concentration, the target concentration value, the value that is measured from the standard procedure, and we take the difference between the two and we try to regress it. If we do this, we observe that tree-based gradient boosting models obtain excellent results. You can see on the right the histogram in green of LightGBM for this case, which obtains an expected error of roughly 1.6%. So this is twice as good as the original result. And in this case, upon inspection, we see no sign of pathologic overfitting. So let me also remark that we could basically expect this type of model to work well due to a series of characteristics. Now, what we learned from this is that using physics models as a baseline for machine learning can improve performance very significantly, and much more than changing the model. And also that for this type of data set, classical machine learning can be used very effectively. Now we come to the last part of my analysis, where we want to try to do without the last part of the measurement, the last phase of the measurement. And this is because actually this measurement after the sample was inserted takes some time, and it makes the instrument slower. And this is an instrument that is used in intensive care and emergency units. So actually we want it to be as fast as possible. So luckily, machine learning provides us with the tools to do a feasibility study extremely fast. All we need to do is to remove the data from after the measurement and try to perform our regression again. So here again, you have a histogram of the results, where in blue you have, as usual, the measurement of the standard procedure, including the data from after the sample. Then in red, you have the result of using the Nernst equation, so the standard procedure without actually using for U0 also the value from after the measurement. And in green, you have the result that we obtained if we take this naive procedure and we add our light GBM regression on top of it. And we see that this brings down the expected error to 2%. With respect to the 1.6% that we had using the measurement after the sample, actually this is only a small accuracy loss that we see here. Now, of course, this also deserves a sanity check. And essentially what we did is we tried to regress not just the target value of the concentration, but we actually tried to regress all of the information collected after the sample, and we obtained excellent results. So this passed our checks, and we concluded that the last phase of the measurement can be skipped with very little impact on the precision to allow for faster measurement. Now, what I would like to point out is also that the whole effort involved in this project was actually quite small. And this is because in the end, all we need to do was a bit of data preparation and a bit of machine learning, which actually went much faster than we expected. The overhead was much more significant. Now, in terms of computational resources also, since we used only classic machine learning approaches, these are extremely fast, and the whole analysis runs in less than 1 hour on a standard laptop. The key take-home messages for carrying out projects of this type are that machine learning can provide very quick answers to feasibility questions, that nowadays public libraries make it very easy to compare many different machine learning models, that for data sets of this type, classic machine learning could still be used very effectively, and that we need to be extra careful when using data that was not collected for the purposes of machine learning. In terms of insights we gained, the error on the concentration could be reduced from 3.4 to 1.6%. And the last phase can be skipped with a very small loss in accuracy from 1.6 to 2%. And ultimately, we also saw that engineering features using physical knowledge can, of course, improve machine learning models, but more importantly, that using physical models as a baseline for machine learning can improve the performance significantly, and probably more than the choice of models for this type of problems. And with this, I would like to thank all of the people that participated in this collaboration between Hochschule Luzern and Roche, in particular Gregor, Corbinian, and Mirko for setting up the project, Martin, who provided the data, and Andren, who worked with me on the analysis.
So I have a question. Can you hear me?
Yes, now I can hear.
Okay, good. Yeah, so thank you very much for sharing your work here. So I have a question that is more about the finding that you had that the linear models, they perform better as compared to tree-based models for this task. Could you explain a little more, like in your perspective, what were the factors that may have contributed to such a finding? Well,
this was for the simple sort of baseline approach where we really tried to regress the whole target by using a model. And it's not very surprising, because in the end, what I told you is that this Nernst equation that rules the basic process that is happening underneath the instrument measurement here was recast in linear form essentially by taking logarithms of concentrations. So all this is telling us is that essentially, if we don't give the machine learning model any additional information, the first thing it learns is that there is a linear relationship, and it cannot really learn much more beyond that if we don't guide it. If we give it some appropriate guidance, things look quite different. This is a bit similar to what people sometimes do. For instance, when you do forecasting by taking differences of time series and so on.
Good. Then a follow-on question is more about the approach for using physics-based models. So the question is that are you referring to using some existing physics models that you embedded as part of your pipeline, or are you using kind of physics model to infer features that would be then better usable in the ML context?
So we're doing, in some sense, both, but less the first one. So I should say we used the physics knowledge about how these time series should look like to try to come up with a reasonable representation to feed our model. So this is a simple, very standard procedure. The thing that is a bit more tricky to realize is that indeed, just by starting with a baseline smart result, which is given by a physics model, we can improve machine learning models a lot. And in this case, we actually don't really need to embed machine learning the physics model within machine learning. We just need to sort of reformulate the problem a bit smartly, and we obtain the gain essentially almost for free, because all we do is regress the difference.